Good morrow, fellow humans. My name is Sean, and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is.
In the last chapter, we unravelled the long tapestry of time, from the universe's cataclysmic birthing through to its eventual heat death a Google years later. But that wasn't the end of the story, as the following photon age then stretched into a future history that was so seemingly endless that it rendered the ages of both light and matter as next to non-existent. But as debilitating as these thoughts can be, there is still one more tiny little detail that we've thus far failed to consider, which is that time passes across an unfathomably broad spectrum of speeds, fluctuating wildly from one point in the universe to another. And so what this shall inevitably mean is that the weaving of time threaded between our own unique now and these far-off ends of the universe will end up being a far more complicated tapestry than what these first impressions may have led us to believe. Though here, or somewhere within this tangled vicinity, is where our descriptions finally arrive at their theoretical ends. But can time end? Did time start? It's a tricky question to answer, especially considering that we don't really know what time is. For when we cast our mind's eye towards these final stages of the universe, to a world where nothing persists but free-roaming photons, it becomes increasingly difficult for us to keep a rational hold on this familiar phenomenon to whom we have given the name time. In 1905, just 2 years after the Wright brothers had famously taken their inaugural flight, and a mere 3 years before the invention of plastic, a young physicist named Albert Einstein taught us that space and time can be thought of as differing characteristics of a single interwoven material, a fabric that warps and pulls against the influences of speed and gravity. A fabric that we know today as spacetime. The upshot of this universal tug-of-war was that the faster any individual moved through space, or the closer they came to a strong source of gravity, the slower their movement through time. What we had learnt from this inspired 26-year-old was that time is unique to the beholder. Time in the International Space Station runs fast, at least faster than it does on the ground. Right now, assuming you're upright, the flow of time at your head is running faster than the flow of time at your feet. It's a real-world phenomenon, though one hardly perceivable from the resolutions of train schedules and wristwatches. However, nowadays, with the invention of satellites and quantum timekeeping, the effects of time dilation have the potential to cause major disruptions. Our global positioning system, the GPS, which we can access from our phones daily without giving it a second thought, is guided by 24 satellites, each in orbit of the Earth at altitudes of 20,200 kilometers. That's 12,550 miles. And they're travelling at speeds of up to 14,000 kilometers per hour, or 8,700 miles per hour. Due to the time dilation caused by the lessened effects of gravity, each satellite's internal clock gains 45 microseconds every day, while due to the warpage caused by its high speeds, 7 microseconds are then taken back, leaving the slightest 38 microseconds to be accounted for if we are to avoid the exponential drift of map coordinates that would allow our little blue beacon to drift off its course by 11 kilometers in only its first day. But it's not all clocks and synchronization, as time dilation could just as easily be used to witness the far distant future. All anyone needs is a spaceship capable of travelling at speeds close to the speed of light. This is because for every minute spent travelling at 95% the speed of light, 3.2 minutes pass on Earth, and if we encroach further upon the ultimate limit towards 99.999999999% the speed of light, every minute of our time would then be relative to almost 1 year and 4 months for all those who were left behind. So, leave home at lunchtime on Sunday and arrive back in time for dinner 480 years later. There is, however, a finite limit to this warpage, as at the actual speed of light, the dilation becomes so intense that it renders the passage through time impossible. And so if we return to our previously described universe of lost and lonely photons, this is the universe we should be imagining. One lost within a single moment of unmoving time. At least, that is, from the perspective of the photons. Because from the point of view of a photon, time is meaningless. Unlike the time we experience, time for a photon is contained within a single moment, frozen within a collapsed dimensionless space. Its entire history is over as soon as it's begun. What this means is that there are photons out there right now, as ancient as the oldest stars and prepared to sit by as the entirety of the universe's history unfolds, that, from its point of view, has not only just emerged, but is already at those universal ends. I know, it's not a thought that sits well, and I can assure you, dwelling on it offers little relief from the perplexity. But it is nonetheless relevant, because it provides us with the context needed to ask the more fundamental question: is there time without change? This unanswered question is one of our oldest on the topic of time, if not the oldest. Indeed, this is a conversation that countless philosophers, scientists, and even theologians have added to across the ages, though it is probably fair to say that none have been more influential than the following three gentlemen. Beginning, as we so often do, with Aristotle. Time is nothing more than the measurement of change as perceived by the soul. And so by the logic of an Aristotelian worldview, no change is equal to no time. But the modern thinker's more palpable take is more commonly taken from Newton. However, this is not because Newton was more intelligent or enlightened, nor even that he had access to a broader wealth of scientific knowledge. No, Newton's thinking resonates so strongly with our own because modern intuitions are inspired primarily by his thinking. For Newton, time is an unwavering force, one which, once set into motion by the hands of an almighty, flows ceaselessly into an ever-oncoming future. Tomorrow is a day away, a year 365 days, and nothing, not even the death of matter, could ever hope to hazard time's relentless ticking. a fact that should remain true regardless of where one is in the universe or what they're doing. And though it may seem like an obvious position to take, the idea that time simply is, it is actually quite a clever and intuitive interpretation that time always moves at the speed of time, whether or not change occurs. But though it's genius, it's also wrong. As Einstein was to show, everything, including time itself, is relative. Because for Einstein, there is no universal tick to time, since each and every particle is only ever moving in time relative to the other particles. But this idea has in some ways brought the intuitions of Aristotle and Newton together, because for Einstein, as it was with Aristotle, change is also crucial. The critical difference is that so is perspective. The flow of time, represented by any rate of change, is only made meaningful when it is considered relative to another reference frame's rate of change. For those on Earth, time feels like it runs at the speed of time. But that's precisely what happens for those on the International Space Station. Only when their relative times are compared can we witness their underlying variances. And as for Newton's part, Einstein shares with him the claim that time acts like a dimensional fabric. The only difference is that for Einstein, the fabric warps. But the more profound lesson to be learnt here is not that time warps or that it's entwined with change. The revolutionary mind bend that is so often taken for granted is that there is a clear disconnect between the time that we experience and the time measured by clocks. From our perspective, time always runs at a fairly steady, though somewhat wishy-washy rate. But according to these clocks, time can flow at intensely varied speeds from one point in space to another. So then, which is the real time? Clock time or experiential time? And if our experiential time must be questioned, what, if anything, can we presume to know about time at all? For everything we know about time is understood within the context of how we experience it. Though Einstein's relativity remains an incomplete theory of time, it nonetheless continues to play the most crucial role in our evolving understanding, resulting in what is perhaps an overabundance of interpretation as each new generation tries to highlight what and how much is actually being said by Einstein and his most widely acclaimed work. One interpretation, often credited to Einstein himself, but should probably be left to his mentor Hermann Minkowski, or if you want to split hairs, the pre-Socratic philosopher Parmenides, is the theory of time known as the block universe theory. The idea behind this model is that due to the interwoven nature of space and time, as space exists omnipresently, so too must time. Meaning that the past, present and future would therefore exist simultaneously. What this is asking us to envision is an objectively real past and future whose present is only a matter of perspective. In this universe, you would not only exist in the present moment, but would be stretched out like the worm inside an apple, with your birth at one end and your death at the other. If this is the case, then time doesn't just wind down alongside the deterioration of matter, for it's been an illusion from the very outset. And as strange as this might sound, it is currently the most widely spread description of time shared among physicists today. There are, of course, some issues with this way of thinking, but we'll get to these shortly. But apart from the timelessness said to be found in this winding down of matter, is another timelessness, found at the other end of this temporal tether in the supposed beginning of time. yet another vision of the universe considered devoid of change and hence beyond time. But this too is a regularly misinterpreted concept. Even in the block universe model, this idea of time having a start is far from readily agreed upon. In fact, the something from nothing explanation that often tags alongside our description of the Big Bang is hardly supported by any of today's major theories. Since the story of the Big Bang first hit the presses in the 1920s, there have been many hypotheses about the nature of before or even after the universe, from bouncing universes to colliding multi-dimensional brains. But the reason why many of us still circulate this idea that space and time started with a bang comes down to a simplified coupling of Einstein's relativity with Edwin Hubble and Vesto Slipher's 1929 discovery that the universe is expanding. By combining relativity with inflation, one could suggest that in order to describe the beginning of the universe, all we have to do is simply roll the clock backwards and watch as matter traces its path back down its current expansion trajectory and into its initial Big Bang singularity, where time and space reach a state of infinite compression and then, as if by magic, cease to exist. It is this exponential compression into infinity that does once again appear devoid of change. But here is where our interpretations often get ahead of us, as at the point of infinite compression, they say, space and time and all that is within ceases to be. But if it comes to an end, then this isn't really infinite. This is why infinite compression is rarely accepted as anything more than just a mathematical conception. Ultimately, the only honest thing we can currently say about this so-called singularity is that it is the point where our equations begin to fail. Because beyond the very finite scale of the Planck length discussed in earlier chapters, there isn't much that can be said with any certainty at all. Of course, this mathematical break may in actuality reflect some absolute physical limit. Still, before we jump to that conclusion, we must remind ourselves of the limitations of mathematics, especially when dealing with infinities. Now, you will probably be happy to hear that I don't intend to dive into any equations or any rigorous breakdowns of mathematical reasoning, as, for starters, that's definitely not within my wheelhouse, though nor is it the point as to why we're here. However, as our shared pause in the crazy does unfold, I do intend to return to the topic and philosophy of mathematics on several accounts, as it will become increasingly important for those willing to follow me on this journey that collectively we gain a better understanding of this often inaccessible language, especially when considering how mathematics has been accredited with an almost godlike status. Maybe this is nothing more than a trope common of ancient tongues whose usefulness survived the millennia, as standing at 3,000 years old, mathematics is considered among the oldest of languages still found in widespread use today. But maybe there's more to it than this. Though why it stands relevant to us now is that at either end of the universe's lifespan, we reach these mathematical infinities, either as the singularity of the Big Bang or as the unchanging emptiness of the universal heat death. Changeless states often said to harbour the start or end of time. And so it has become necessary that we now determine whether we need to distinguish between a fundamentally mathematical idea of infinity that sees it as a solution to an equation and the conceptual infinity that we might use to imagine a foreverness of reality. So that's what we're going to get into next week. We'll take a moment to look into these difficulties before getting back into what they say about our understanding of change and time.
Good morrow, Infinity lovers. Thank you so much for sticking around to the end of the film. I hope you enjoyed it. This little bit at the end, I give a bit of a preview as to what we can expect over the coming weeks, and also address a few of your comments that have been popping up. First and foremost, we've had a bit of a upsurge of interest of late, and that's been amazingly exciting, and it's also been very soul satisfying because your messages have been just so beautiful. I will make sure that I take the time to respond to each of you, especially the ones that are deciding to wax lyrical about philosophical ideas. I'm happy to be challenged. I'm happy to start a bit of a discourse with you one-on-one. So let's do it. Let's get into it. Let's try and break down some boundaries. The content that we currently have this month, it's going to be 3 chapters that are part of one grander thought. So this week we're doing the ends of time, and next week we're getting into more of a similar idea, but the mathematical infinities, and we'll talk about infinite sets and your Cantor's thinking, and then in the end wrapping up this idea of big bangs and points of infinite compression, and see how the materialist view and the scientific view can inform a more metaphysical understanding of reality. That's what's there. That's what the week is. If you want to follow that story, watch us week by week, or you can go into our playlists. There is just the episodes playlist now, and there's also the full chapter playlist. It will be added to the full chapters playlist at the end of the month as one piece. That's what it's there for. I'm going to leave you. I don't want to take up too much of your time, but thank you so much for jumping on board, for leaving your comments, and letting me know that there is a community out there. So much love, and I hope you have a wonderful week. All right, bye. Boop.